Hello folks, thank you all for coming. It's very nice to see so many faces. It's been really lovely this weekend seeing so many people that I recognize, new people. It's been so fab. Thanks Pamela, for introducing us. I'm Harrison, this is Fred. We're from Climate Policy Radar, and we're going to be talking about building a knowledge graph for climate policy. We're going to talk through the full pipeline, end to end, how we've built this thing. But to start, who are we? What's Climate Policy Radar? What are we doing? Climate Policy Radar is a non-profit. We build open databases and research tools for governments, researchers, international organizations, private sector, civil society, to understand, analyze, use, discover insights about climate policy. We try to bring together lots of previously inaccessible data, legislation, policy, and add structure to it so that it's more discoverable. And in practice, for the time being, that looks like this. We're essentially a search engine for now. You can come along to our website, type in the word flood, and discover stuff about floods. If you click on one of those search results, you can see where in that document floods are mentioned and how, which is great. We have documents from 200 governments around the world, about 27,500 documents, 2 million pages, 45 million passages of text, 350,000 users a year from all over the world who spend a lot of time on the site, which is great. It works. People like it. It's working. So why a knowledge graph? What are we adding that we don't already have? These statistics are fine. They're great. They're wonderful. But there's a kind of more important fundamental here that isn't on the slide, which is this. That at the moment, there's only one way to explore this data. It's fantastic if you already know what you're looking for. But if you're new to the climate policy research space, if you don't know the landscape, if you don't know what to look for, what's interesting, how two things are related, traditional search is kind of falling short for that kind of exploration and discovery. Ideally, we want to allow users to browse our library of documents. And users tell us that ideally, if they're going to browse, if they're going to move laterally through the collection, they would like to do it by topic. Two documents being topically related is a pretty good bridge between them. So let's do that. Let's imagine creating a topic here, and imagine marking every time that concept is mentioned in a document. Maybe the concept of a flood. Let's go and read through every single document, every single passage of text in every single document, and add a little sticker to those passages where we recognize a flood being mentioned based on this definition. We could do that manually. Currently, the climate policy research landscape does do a lot of this stuff manually, by hand, with research assistants. It takes an enormous amount of time. But a lot of us here are data scientists. We know that this is a pretty standard named entity recognition task. So we can do some named entity recognition. That's fine, we know how to do that. Why is that different to, what do we get from making this a knowledge graph instead? In my mind, the simplest way of describing what a knowledge graph is named entity recognition plus some superstructure, some structure that joins those concepts that we're looking for together. We know that concepts don't exist in isolation as little floating islands. They are connected to each other. They have semantic links between them. The simplest way of illustrating that is with hierarchy. We can imagine that coastal floods are a subconcept of floods, and every time we recognize an instance of a coastal flood, we can also say that is an instance of a flood. And every instance of a flood we can also label as an instance of an extreme weather event. By defining multiple classifiers to recognize instances of many concepts that are connected in this way, the insights that we get from them start to compound. But hierarchies have some pretty severe limitations. I think anyone who has tried to work with hierarchical data like this has experienced this problem. That the real world is messy, it's complicated. The world of climate policy particularly doesn't really fit into these neat, linear, hierarchical structures. People come at the climate policy problems from multiple perspectives. I described all of those different audiences: civil society versus people interested in litigation, policymakers versus the private sector. And ideally, we want to be able to model all of those perspectives. For one person, the concept of sea level rise might be an instance of a marine hazard, and for someone else, it's a slow onset event. Ideally, we want to be able to capture both of those things. In addition to that, we would ideally like to be able to represent the non-hierarchical relationships between concepts. For example, the link between deforestation and flooding. There is a link there that a lot of people recognize and is important to be able to demonstrate to our audience or allow them to use. But this hierarchical scheme doesn't really enable that. It's limited. So we allow for that hierarchy to break and bend where it's appropriate. We allow for concepts to be related to each other through these looser, more associative connections that break out of those hierarchies. And because those concepts that are related to one another are just concepts themselves, the same rules apply. So they can also sit in their own hierarchies. And because those other concepts in those other hierarchies are also just concepts, they can also have these looser, more associative connections between them. And already, I think you can see quite a complicated graph building up here, complicated network of ideas. Also, we allow for concepts to sit in multiple hierarchies to enable that thing that I was talking about earlier. Yeah, as we scale up this process, a graph begins to emerge. Attaching classifiers to all of these things, yeah, a lot of complexity begins to emerge. So I hope I've already illustrated the sort of nuance that this kind of system is able to capture, especially with those extra classifiers attached. So, concepts. How do we define those concepts that are going to sit in our knowledge graph? We have the kind of intellectual frame, the ontology, for capturing those concepts, but we need some actual real things. How do we do that at CPR? Humans, human experts. We have an internal policy team who have deep backgrounds in climate policy, and we ask them to define the concepts for us. They tell us what is important, what's significant, what's influential. We work closely as data scientists, data engineers with that policy team on a daily basis. We've seen a lot of modern approaches to building knowledge graphs that are fully automated, fully hand over the process to an LLM, which is great, it's fine in most contexts, but the sort of high risk, high impact domain that we're working in, we don't feel like we can abdicate our responsibility, our institutional perspective to an LLM. We get a lot of value from that expert opinion. Yeah, the stuff that Fred and I are talking about here today, all of the fancy machine learning pipelines and data infrastructure, is not really the core value of what CPR does, Climate Policy Radar. The real value is in that human expertise. Our jobs are just to scale that expertise, scale the impact. So we're using these humans to define which concepts are important. How do we do that? We're using Wikibase. If anyone has come across Wikidata before, Wikibase is essentially Wikidata without any data in it. It's an empty shell that you're able to populate with your own ideas, your own concepts, your own structures. Wikidata is a really fantastic example of building this kind of knowledge graph at scale, They've done it for a decade. They've incorporated millions of nodes, billions of edges. While remaining open and discursive and auditable, it's all very, very transparent, which are all things that we aim to be as well. And by using their technology, we also inherit a whole set of community best practices, norms, which have helped Wikidata to thrive and have also helped us to have those sorts of discussions, debates, back and forths about where the boundaries between concepts exist. This is an example of a concept in the concept store. This is a flood, or a Q382, which allows the policy team to add a quick description of the concept, a stricter definition with links to authoritative sources, a set of aliases, and a set of relationships to other concepts in that frame that I talked about earlier. And allowing our policy team to kind of run wild in Wikibase for about a year, we have ended up with this, which is our kind of first stab at a map of the climate policy landscape. This is about 1,500 concepts that are all linked together in that way that I talked about earlier. It's quite pretty. So that's how we build concepts. How do we turn those into classifiers that can go and find instances of those concepts through all of our climate policy documents? I hope these illustrations are illustrative enough. They're quite basic. We have the concept store, our Wikibase instance. We can pull concepts out of that, like our concept of flood, as an object that we can manipulate in Python. We then hand our concepts to what we call a classifier factory, which makes determinations about the best classifier to use based on the context of that concept, the number of relationships it has, the length of the description, the number of aliases, the number of training examples attached to it. And out of that classifier factory pops a classifier with that concept inside it. It's a one-to-one relationship between concepts and classifiers. For example, this one for the flood might be a keyword classifier, but for a more nuanced concept where the boundaries are kind of blurrier, we might use a BERT-based classifier or a spacing model. And for an even more complicated one, we might use an LLM or some special magic classifier that is yet to be invented. The point is that it's kind of a black box. The classifier structure is common to all of these things. So when we hand them over to the data engineering team, the way that they use them, the way that they scale their use is the same for all of these classifiers. The other major point here is this, that there is a separation of concerns between the policy team's work and the data science team's work. The policy team can focus on creating accurate representations of those concepts, accurate descriptions, the right set of relationships between all of these things. And the data science team can focus on the appropriate choice of classifier for that concept. In general, we try to use the smallest possible model that delivers the best possible performance, both for idealistic reasons, I suppose. We want to minimize the negative climate impact of our work while maximizing the utility to our users. But it's also a strategic choice as well as an idealistic one. Smaller models tend to be more interpretable, so defaulting to those smaller models where performance is equivalent helps us with debugging or improving those models. So we have a set of classifiers now for each of these concepts. How do we know that they're producing reasonable results? Again, you might be surprised to hear we lean on our policy colleagues. Again, we don't feel like we can abdicate our responsibility for evaluating these things to LLMs. There are a lot of nuances in this kind of technical domain that LLMs we've seen are not able to get correct. So we lean on this group of policy experts. Each model is validated by multiple human experts through a very, very similar labeling exercise. We use Argia to label instances of each concept in passages of text sampled from our real dataset. Having that dataset allows us to then evaluate every model, every candidate model thereafter, so that we can make those choices about model size versus model performance. We sample passages quite carefully, both because our policy team's time is valuable. They're a small team, they have a lot of work to do. But also, that careful sampling allows us to check the biases of our classifiers. We have an enormous number of documents, and we want to make sure that the performance of each of these classifiers across all of those different document strata are equivalent. Not only that the performance is good, but that it's stable. So we check across geographic region, World Bank regions. We also check the translation status of those documents. All of them are translated into English before we process them. So we sample a set of both translated and non-translated text. And we also check document type. That is litigation documents versus policy documents versus corporate disclosures. But as data scientists, we know that metrics are really just reflections of human preference, and they're quite poor reflections quite often. Unless you really get the data right, metrics are fallible. So we also run these qualitative vibe checks of the classifier outputs through a tool that we have been calling the vibe checker, that allows the policy team to run through a whole set of predictions on a sample of the corpus, checking whether the results kind of match their expectations, match the definitions that they had input into the concept store. Ultimately, we would like to do away with this vibe check process in addition to the metrics. We would like to align the metrics so that the vibe check is not necessary. But for now, while we're still in this kind of growth phase, it's been really useful to have both. So that's evaluation. At this point, we have a process for defining new concepts, building classifiers around them, and feeling confident that they're performant and fair, and also finding mentions of all of those concepts in arbitrary blocks of text. But now comes the hard part, scaling that work to the full corpus, which is what I'm going to hand over to Fred to talk about.
Amazing. Thanks, Harrison. As mentioned, I'm Fred. I'm the tech lead of the platform team. We're responsible for building some of those underlying building blocks and structures that then other teams can build upon. So the data processing behind all this is a key concern for us. We want it to scale in terms of its DevX, its reliability, and its speed as well. I'm going to give you a bit of an insight into what developing that has been like. And it's probably worth mentioning that we've come a long way, but also we're feeling very much like we're still at the foot of the mountain, and the summit is quite a distance off. So I'll be giving you an insight into where we want to go, as well as what we've done. This is where we are today. So we want to relate this knowledge graph to our documents, and essentially we're talking about a text classification pipeline. You can already see some of the things that Harrison has touched on there, with Argia and Wikibase being brought together to train classifiers. We run inference over all of our passages, and ultimately we load them into our search database, which we're using Vespa for. Let's start working through that and talk about training. How do we scale training? And the key thing I would say about this is if you want to build a car, you need a production line. So we're talking about factories here. We want to end up with over 1,000 classifiers before too long. So we need to think about managing the process. Training is dynamic. Source data in Wikibase and Argia will change. Models will be replaced. Parameters will be tweaked. Our data scientists and subject matter experts work closely together to define a concept, build a classifier, move from simpler models as a baseline to more advanced ones. The models are promoted through different environments as we get more confident in them. And we also need to manage the way we reference those classifiers. There's quite a lot that happens, and we need to make it easy. Our factory, our production line for that today is a CLI. This lets us abstract a lot of the details, making it easy to just train by running a command. And already, this repeatable process has got us to 80 classifiers. But as mentioned, we want thousands. At the moment, classifiers are actually still trained on individual machines, on our own laptops. And that's siloing our metrics and making computer bottleneck. So before long, we hope to have an automated pipeline for training that can progress and score and be reviewed remotely. When new data comes in, it can just be re-triggered. It could then confirm the metrics and promote through the different environments. That was training. Let me talk about inference and indexing. There's quite a scale to this, and because of that, we had some challenges around it. We want to run each classifier over all of our text and load into our search database. Now, while I've been thinking and working on this, I've been thinking about something called the weight calculation, which if you've never heard of that, you're probably not a massive nerd. The weight calculation is something we think about in space travel, in science fiction. And it's the idea that if you were to set out today to a distant galaxy, on your way there, technology and understanding would develop back home, such that a future generation of space travelers could overtake you and arrive at the destination before you. Funnily enough, we had a very similar thing happen with our pipelines. Our early version of just indexing, we worked out would take 137 days to run, which would still be running as I'm giving this talk from when that version was created. So obviously we had a lot of room for improvement there, a lot of room for future generations of those pipelines to get faster. Pleased to say it now takes less than a day to run over our whole corpus for the whole pipeline, not just indexing. And the major improvements around that to our technology and understanding came in two areas. So the first one, the biggest impact, was the concurrency. This is a view from our orchestrator. We're using Prefect to manage the tasks. Those lines are batches of work, basically. And you can see already that we're thinking about concurrency. You might also be able to see a problem. I like to call the problem the background. There's a lot of empty time when nothing is happening. The reason for this is that we have, each of these represents a document. One of our documents is a single page. Many of them are 2 pages. We do have documents that are more than 2,000 pages. So running in batches like this, you end up with very little happening at the end of the batch. You can see the results, the impacts of that on CPU usage in Vesper as it spikes at the start and then peters off. What we really want is to color in that background, which is what we now do. We move to a more interleaved approach that starts a batch as soon as there's space to start a batch. I mean, you can still see a bit of the background. We've got ideas of minimizing those like cold starts. I'm not expecting the impact to be as substantial, but this doubled our runtime. No, the other way. That can happen. This halved our runtime. Second area that we saw some massive speed ups from was rethinking the way that we handle the data before it gets loaded into Vesper. At one point, we were updating Vesper once for every classifier for every document, which means when we went to 2 classifiers, that doubles the runtime, doesn't half the runtime. That was great when we had 1 classifier. When we kind of started getting a lot more classifiers, it started being really painful. So a better approach, simply changing the way we consider our looping logic, was to move to aggregating all of the inference results for those classifiers first. So we introduced a step that did that before loading them in. And this actually also has really nice idempotency gains. We're just pushing down the desired state onto Vesper. We don't need any complicated logic to think about what is currently in Vesper. We just push the latest into Vesper, basically. That's where those have been huge. As mentioned, we've gone down from 137 days to run over all of our data to less than 24. We would like to go further. There's some good incremental gains I think we can get out of some of that. And also moving to a more incremental approach, I think will also make this even better experience. So that's still to come. Next thing I want to talk about is observability. And at this point, I'd like to tell you an embarrassing story. I went to the cinema recently with a friend, and I was rushing from work, so I hadn't had any dinner. And I managed to miss a series of warning signs that I was about to embarrass myself. Because there were 3 clues that I didn't pick up on. My cinema has recently got a pizza van inside the cinema, and you can order something to come to your seat. I thought, great, dinner's sorted. I'll rush over, I'll get in the queue, and I'll order it, and they'll bring it to my seat. But when I arrived, there wasn't a queue. That's a warning sign that something wasn't quite right, and I didn't pick up on it. I went and ordered my pizza, and they gave me a look and were like, how many people is this for? I'm like, well, just me and my friend. And they looked shocked. That was warning sign number 2. I then went to pay and was pretty shocked at how expensive it was. And I kind of just assumed this was the classic cinema marking up the price situation. But that was actually warning sign number 3, that something was wrong. I went and sat down at the cinema. After 10 minutes into the film, the kind of settled in, busy opening night, full packed cinema. Suddenly, out of the side of the cinema emerged the biggest pizza box I've ever seen, being struggled to be carried by multiple people as it emerged slowly towards me, sat in the middle. Everyone in the cinema locks onto this pizza, watches it come over to me, and they're like, did you order a pizza? I'm like, I really want to say no, but yes I did. That is my giant pizza. And I then had to try and work out how to not distract everyone from the film when I couldn't even open the box without blocking out the screen. My family and I ate pizza for every meal for the rest of the week. Point is, if you don't pick up on clues, on warning signs, you can end up with a catastrophe. In much the same way, we now make it very hard to miss clues in our pipeline. We bake in the principle that we want to have those early warning signs before we embarrass ourselves. And some of how that looks today is through collecting up all the failures, balancing our logging to get the right information without too much noise, and alerting in Slack with a link to the error message in the Slack message. This is one of our reports at the end of our Inference, saying which classifiers run successfully, and also like surfacing which ones there were problems for. This is deliberately made available as a JSON object, which we can load into our observability tools, our data lake. And through those, we also hope to be able to eventually be comparing across both different like historical runs, but also different parts of the process. And I'd like to end up with a nice visual dashboard for all of this that we can give to our non-technical people, and they can also see where things are. Yeah, there's another, yeah, great, that was it. So in conclusion, scaling classifiers requires a production line, build a factory. Pipelines can get faster with each generation as the code base develops, the technology and understanding grows too. And pipelines need good observability, as do people when they go to the cinema. Let me talk a bit about the results of all of this. So we talked about the context of our knowledge graph, how we've scaled it. I'm just going to give you a quick preview about what we're hoping to get live this week is a change to our search experience. where we would allow people to be able to come and choose which topics they're interested in, concepts. The ability to see that aggregated at the top of at a document level, and then also to navigate documents at the passage level according to their concepts they're interested in. This is kind of like our current milestone in terms of climbing that mountain. There's a lot more we want to do around graph analysis, LLMs, integration, and other fun stuff. But that's all we have for today. Maybe we'll come back next year and talk about that stuff. As mentioned, this is the link to our knowledge graph. You can actually go there and start learning about floods, cliff stabilization, other things like that. And we like working in the open. This is a link to our code, warts and all. And if you really like talking to us, maybe you can consider coming and working with us. This is our careers page as well. But I'd like to thank you all very much from me and Harrison. And yeah, we'll do some questions if we've got time.
Thank you. Thank you so much for that insightful session. Does anyone have any questions?
That's very nice talk. So with all these classifiers, did you analyze what's the difference? I know you went into flexibility, but what's the difference of having like one big classifier, or at least all the batch-based ones, that just one, instead of having that many in terms of like maintainability and performance?
I've got a big slap, but do you want to go first? You go.
Oh,
go.
No. Always try to defer to the data scientist. I think from my perspective, it's really useful from like a scalability perspective. You can have a logical mapping from the concept to the classifier, and you can score that in its own in isolation. So if classifiers overlapped a lot more, maybe we make some improvements and now they're much better at floods, but they've just got worse at cliff stabilization. I don't know why I'm reaching for those two examples. Whereas having that like a more of a that production line, it links everything up nicer in a way that we can scale it up faster and easier. Do you want to add a more data science nuance?
Yeah, no, that is roughly my answer as well. But my mind goes more to the actual training of these things, actual optimization. It's easier to work on one problem at a time. Yeah, and only consider one evaluation set without worrying about the harmful effects on others. Yeah.
First of all, thank you very much for a very insightful presentation. I don't know if you can spend just a bit of time at a macro level, just kind of explain a bit more on how you guys have parallelized this problem. I think you indicated that you use prefects.
Yeah, that's right. Yeah.
And I just want to know a bit more about how you've kind of gone about that architecturally. Thank you.
If you're extremely interested, this is a good place to go. I think the approach that we've taken has gone through several iterations. I guess that kind of came through in the talk. There's some nice out-of-the-box concurrency that we were initially using with Prefect, but as the nature of our data and what we were trying to do with it proved, we wanted to go beyond that. And so without going in too much into it, we're currently using a semaphore object to keep track of how many open spaces we have to run batches. We run like a lot of kind of async stuff as well. And one of the principles that we've tried to take is that if you want to do things concurrently, you need to be good at doing it sequentially. And if you want to have to debug a concurrent flow, you're debugging something much harder. So basically trying to get it right, running one way, and then looking at how it can be moved across. So that's also taken the form of running on like multiple hosts, as well as, so like initially running across multiple threads and then expanding to multiple hosts, and but getting it right in the simple so that we can then, yeah.
Thank you.
Thank you. So we can just take one more question.
Thank you so much for your talk. This is very interesting. So my question is more related to the final product rather than the underlying method, because I'm very interested in using your tool for my future work probably. So I'm wondering, can you give me some illustration or example of how this, all the things you have done have made this search, say a certain topic or something, better than would have been if we don't apply the method you use here. Yeah.
Do you want to talk about this? Or,
Sure.
Yeah.
Yes. We have a team of internal policy experts who have long backgrounds in doing climate policy research. We use them as kind of super users of the tool to get feedback. We also talk to lots of external users. Traditional search runs as a hybrid search. It's lexical and vector-based. So it's primarily keywordy, but we also get a little bit of fuzz around the edge to match other keywords that people might be using. The nice thing about this is that if you are looking for floods, we have a very, very tightly contained set of terms or a model that captures much more precisely the semantic space around the concept of floods. So your search results for these important or significant concepts are much higher quality than you would get through traditional search. I think I mentioned at the start that one of the use cases that we imagine for this is people who are interested in multiple concepts and comparing those. The errors across multiple searches or multiple concept filterings compound. So the high quality kind of bounding of those spaces matters much more as you add more and more concepts. Yeah, that's the kind of simple answer. I think there are many, many more improvements or interesting pieces of analysis that you can do on top of this graph as an artifact in and of itself. We've tried to keep that out of this talk, but that is the long-term ambition for this, is that it's not just a new interface to search, but an artifact for analysis in and of itself. Being able to find important, significant hinge concepts in the climate policy domain for further work. Yeah.
Thank you. An amazing session. Thank you, Harrison. Thank you for the end of this session.